Take a look at these three clear, colorless liquids sitting in these vials. On a molecular level, they are almost identical. They all contain carbon, hydrogen, and a single nitrogen atom. They might even smell somewhat similar, a pungent, fishy aroma that is characteristic of the organic nitrogen compounds we call amines. But despite their physical similarities, these three substances behave fundamentally differently in a chemical reaction. One might react vigorously with a reagent, while the second reacts slowly and the third doesn't react at all. These are primary, secondary, and tertiary amines. The distinction between them isn't just a matter of academic labeling. It's a pillar of organic chemistry that dictates how drugs are synthesized, how dyes are created, and how biological systems function. But here's the puzzle. If they all look and smell the same, how do we actually tell them apart in the lab? Today, we are going deeper than just memorizing a list of tests. We're going to look inside the molecules to understand why certain structures allow for specific reactions and others don't. We're going to explore the Hinsberg test, the nitrous acid test, and the carbamyl reaction, not as steps in a recipe, but as logical consequences of molecular geometry and electron density. Before we look at the tests, let's build a rock-solid mental model of what we're dealing with. Think of an amine as a derivative of ammonia, NH3. Ammonia is a nitrogen atom bonded to three hydrogens with one lone pair of electrons sitting on top like a crown. To make an amine, we start swapping those hydrogens for R groups, carbon chains. A primary amine, 1 degree, is like ammonia, but we've swapped one hydrogen for a carbon group. It has 2 hydrogens left on the nitrogen. A secondary amine, 2 degree, has swapped 2 hydrogens for carbon groups. It has only 1 hydrogen left. A tertiary amine, 3 degree, has swapped all 3 hydrogens. The nitrogen is now bonded only to carbons. Notice the trend here? As we move from primary to secondary to tertiary, we are losing active hydrogens on the nitrogen and replacing them with bulky carbon groups. This creates 2 major changes: chemical reactivity and steric hindrance. Those remaining hydrogens are the key. They are the handles that reagents grab onto during a reaction. Let's start with one of the most elegant methods in the chemist's toolkit, the Hinsberg test. Imagine we have our 3 unknown amines. We add a reagent called benzene sulfonyl chloride. Picture this molecule. It's a benzene ring attached to a sulfur atom, which is double bonded to 2 oxygens and single bonded to a chlorine. This sulfur atom is electron deficient. It's hungry for electrons because the oxygen and chlorine atoms are pulling electron density away from it. Now remember that lone pair on our nitrogen? That's a concentrated cloud of negative charge. In the Hinsberg test, the nitrogen's lone pair attacks the sulfur atom, kicking out the chlorine. This forms a sulfonamide. But here is where the classification matters. Let's look at the primary amine first. It attacks the sulfur and loses one of its 2 hydrogens to neutralize the charge. The result is a sulfonide that still has 1 hydrogen bonded to the nitrogen. Notice the environment of that remaining hydrogen. It's right next to a sulfonide group, a massive electron-withdrawing machine. This makes that hydrogen highly acidic. If we add an alkali solution, like sodium hydroxide, to this mixture, the base will pluck that acidic hydrogen right off. This turns the molecule into a salt, and salts are generally soluble in water. So, for a primary amine, you see the sulfonamide form, and then it dissolves in the base. It disappears into a clear solution. Now, let's look at the secondary amine. It also attacks the sulfur and kicks out the chlorine. But because it only had 1 hydrogen to begin with, it has 0 hydrogens left once the sulfonide is formed. There is no acidic hydrogen for the sodium hydroxide to grab. The molecule remains neutral and insoluble. On your screen, you'd see a cloudy precipitate or an oily layer that refuses to dissolve no matter how much base you add. Finally, consider the tertiary amine. It has no hydrogens. It might try to attack the sulfur, but there's no way to stabilize the resulting positive charge by losing a proton. Additionally, the 3 carbon groups around the nitrogen create a shield of steric hindrance. In most cases, the tertiary amine simply doesn't react in a meaningful way. If you add acid afterwards, the tertiary amine will dissolve because it forms a simple quaternary-like salt, but it won't form the sulfonide. So, the visual summary of the Hinsberg test: primary amides yield a clear solution in alkali. Secondary amides yield a stubborn precipitate. Tertiary amides don't form the sulfonamide at all. It's a logic gate based entirely on how many hydrogen handles were available. Let's move to a test that is perhaps a bit more dramatic and arguably more chemically complex: the nitrous acid test. Nitrous acid, HNO2, is unstable, so we have to make it in situ by reacting sodium nitrite with hydrochloric acid at very cold temperatures, usually in an ice bath. When these react, they generate the electrophile we care about, the nitrosonium ion, NO+. This ion is a powerhouse. It's a nitrogen atom looking for electrons. When a primary aliphatic amine meets nitrous acid, things get chaotic fast. The nitrogen of the amine attacks the nitrosonium ion. Through a series of proton shifts, which we call tautomerization, it eventually forms a diazonium salt, Rn2+.
But aliphatic diazonium salts are incredibly unstable. The N2 group is one of the best leaving groups in all of chemistry. It wants to be a gas. Almost immediately, the molecule falls apart, releasing nitrogen gas. Visually, this is unmistakable. You see brisk effervescence, bubbles of nitrogen escaping the liquid like a freshly opened soda.
However, if the primary amine is aromatic, like aniline, the story changes. The benzene ring shares its electrons with the N2 group through resonance, stabilizing the diazonium salt long enough for it to survive at cold temperatures. To prove it's there, we add something like beta-naphthol, and we get a vibrant, beautiful orange or red dye. Now, what about secondary amines? They follow the same initial path. The nitrogen attacks the nitrosonium ion. But they only have one hydrogen. They can't undergo the multiple proton shifts required to form a diazonium salt. Instead, the reaction stops early, forming an N-nitrosamine. These are typically yellow, oily liquids that separate out from the water. If you see a yellow oil forming instead of bubbles, you're looking at a secondary amine.
And the tertiary amines? Their reaction is even more subtle. At cold temperatures, they usually just form soluble nitrite salts. They dissolve, but nothing much else happens. If it's an aromatic tertiary amine, the nitrosonium ion might attack the benzene ring itself, typically at the para position, creating a green-colored compound.
Let's pause for a second and address a common point of confusion. Students often ask, why can't I just use the smell or the pH? It's true that amines are basic. They all turn red litmus paper blue. But their basicity is often too similar to distinguish them in a simple lab setting. And while their smells do vary, primary amines often smell like rotting fish, while tertiary amines can smell slightly more like ammonia. Relying on your nose in a chemistry lab is never a definitive manual for identification. We need these chemical stress tests to force the molecules to reveal their true structures. Now, if you want a test that is absolute, a yes or no switch, you look at the carbamyl reaction. This test is specifically and exclusively for primary amines. In this reaction, we heat the amine with chloroform, CHCl3, and ethanolic potassium hydroxide. The base reacts with the chloroform to create a highly reactive species called dichlorocarbene. This carbene is electron-starved and ravenously attacks the nitrogen of the primary amine. Through an elimination process, the amine is converted into an isocyanide, also known as a carbamyl. You don't need a complex sensor to detect this. You will know it has happened because isocyanides have a smell that is legendary in the world of chemistry for being absolutely foul. It is often described as nauseating or unbearably pungent. Secondary and tertiary amines simply cannot undergo this reaction because they lack the two necessary hydrogens on the nitrogen to complete the elimination steps required to form the triple bond of the isocyanide. Now that we've seen the how, let's look at the why from a different perspective. Why does the number of hydrogens matter so much? In organic chemistry, nitrogen is a bit of a chameleon. It has that lone pair, making it both a base and a nucleophile. But every time we replace a hydrogen with a carbon, we are doing two things. First, we are changing the electronic environment. Carbon groups are slightly electron donating. You might think this makes the nitrogen more reactive, but the second factor usually wins out: sterics. Three carbon groups around a nitrogen atom act like a physical barrier. Large reagents, like the ones used in the Hinsberg test, simply can't get close enough to the nitrogen to react effectively. This is why tertiary amines are often used as non-nucleophilic bases. This leads us to the real-world applications. Why does this differentiation matter to a pharmaceutical chemist? Consider the synthesis of a drug like lidocaine, or even basic painkillers. Many of these molecules contain amino groups. The reactivity of the drug, how it binds to a protein, how it's metabolized by the liver, how it dissolves in the blood, depends entirely on whether that amine is primary, secondary, or tertiary. Primary amines are often anchor points. They are reactive and can be easily modified. Tertiary amines are often used to modulate the pH of a drug molecule or to ensure it can cross the blood-brain barrier without reacting along the way. By using the tests we've discussed, a chemist can verify at each step of a multi-week synthesis that they have created the correct intermediate. If you were trying to make a secondary amine and the Hinsberg test gives you a clear solution in alkali, you know immediately that your reaction went wrong. It's also crucial in the dye industry. As we saw with the nitrous acid test, primary aromatic amines are the precursors to azo dyes. These are the compounds that give us the vibrant yellows, oranges, and reds in our clothes and plastics. If you don't have a primary amine, you can't form that N-double bond N bridge. So, let's synthesize everything we've learned. When you are faced with an unknown amine, first, think of the hydrogens. They are the chemical currency of the nitrogen atom. Primary amines have two hydrogens. They are the open books of the group, reacting with almost everything, forming soluble sulfonamides, releasing nitrogen gas, and creating the foul-smelling carbolamines. Secondary amines have one hydrogen. They are the middle ground, forming insoluble sulfonamides and yellow oils with nitrous acid, but refusing to participate in the carbamyl reaction. Tertiary amines have no hydrogens. They are the shielded members, often staying quiet in these tests, failing to form sulfonamides and staying clear in nitrous acid. Understanding these tests isn't just about passing an exam. It's about learning to read the subtle language of solubility, gas evolution, and molecular geometry. It's about seeing the invisible handles of the hydrogen atoms and understanding how they dictate the behavior of the world around us. The next time you look at a structural formula for a complex molecule, maybe a caffeine molecule or a neurotransmitter like serotonin, look at those nitrogens. Count the carbons attached to them. Now, you're not just looking at a letter N on a page, you're seeing the potential for a reaction. Chemistry is the art of distinguishing the similar. And in the world of amines, these tests are the brushes and the nitrogen atom is the canvas. I hope this deep dive has given you a more intuitive sense of how these molecules breathe and behave. Keep exploring the patterns.